Good afternoon. I'm very happy to be here. I would like to thank you, the Geological Society, the Società Italiana Gallerie, for this interesting event. I'm going to give my presentation titled Structural and Geotechnical Monitoring for Infrastructural Asset Management, New Perspective. It's the last presentation of this day, so I hope you are not too bored. I will try to make it as fun as possible. Just a quick introduction of myself. I am a lecturer in remote sensing and geological risk at the University of Rome, Sapienza. Just a few other notes. I'm strongly involved in monitoring in several ways. I'm one of the founding members of the TC 220 of the International Society of Soil Mechanics on the field monitoring and geomechanics. So that's one topic I'm dealing with. I'm involved also with the PIARC, World Road Association, in earthworks, trying to push the role of monitoring for this. And I'm here as also CEO of a spin-off company of the university named NHAZCA. It's a company dealing with monitoring by new technologies, especially remote sensing technologies. And I am the co-organizer and co-director of the international course on geotechnical and structural monitoring. Just a few words about this event, as is becoming in the last years one of the most relevant events on this topic, on the few. In the last 6 years, attracted more than 600 people from more than 50 countries around the world, and I really hope you will have the chance to enjoy it in the future. A few quick words about NHAZCA. It is a spin-off company, as I already told you. It's a company dealing with remote sensing, mainly satellite and ground-based technologies for asset management purposes and for design and consulting by using monitoring and remote sensing technologies. Let me start with the presentation and with a few words about monitoring. When we talk about monitoring, I'm used to say that there are three main reasons to talk about. The first one is to know, is what I call knowledge monitoring. The second one is to control something, that is control monitoring. And the third one is emergency. In the frame of this event, probably the one that I consider more suitable is the number one and number two. Hopefully we have not to arrive to the emergency case, but these three types in some cases are consequential. If we don't take enough good monitoring and we don't know how things are going, we do not control, we need to arrive to the emergency at the end. Several remote sensing technologies that are listed in this slide show how they can be used for different applications that you can see here, from the design phase to the standard maintenance to the extraordinary maintenance. In general terms, I think that we can do a lot of predictive maintenance by using this technology. And I really hope that in the future, monitoring as a tool for knowledge will be much more used than is right now. So you will see several cases, and we'll go through some cases to present how this technology can be useful in our field. But at the same time, most of them are in the design or in the construction phase. But I really know that in the next years, I will have more chance to present cases for the asset management case. One remote sensing, from my point of view, is quite simple. You can look things from far, have a big picture. You can have a lot of information density. You can go back in time. That's crazily useful. Going back in time by satellite, this is possible. It's very, very effective for several cases. And as a drone, for example, is a great tool for reaching areas that is not reachable by our hands or with our eyes. Main remote sensing technologies in our world are listed here. I will go into detail on the last three, so terrestrial, satellite, radar interferometry, and photo monitoring, as they are probably less commonly known. Let's start with the first one. The first one is satellite. Sorry. Continue. Anyway, this is just a satellite that is moving along the Earth, collecting images every week or every day. Catch information about information is present on the ground and structure. And you can clearly imagine how this can be used. especially if you consider that there exists data in the 90s. So there are today something like 30 years of database of data available to catch information about the past. But there are also a lot of satellites available to make future monitoring. I think today there are more than 10 satellite SAR missions that can be used for detecting millimeter displacement on the ground with a weekly update. That's really something very useful. But what I think is much more interesting is what is shown in this picture. You can go back in time and you can have today a vision of what's happened in the past, and that's very important, especially in the design and maintenance phase. Other good reasons for this technology is cost effective, especially if when you look to large areas, the cost become something like nothing, let's say less than €1 per point or few euros for square kilometers. It's fully remote, so you don't need any installation on the ground. Sometimes it's growing so much. A lot of space agencies and private companies are using managing missions, and so these satellite missions will be much more present in the future. So it's something that will increase. How this can be used? I want to start with this case. This is nothing related with tunnels, but it's related with a transportation asset where in Colorado, USA, the Department of Transportation decided to use satellite INSAR technology just to identify potential hotspot of deformation in the area that could help them to manage their inspection and their budget for repairing and maintenance. That's an example of a huge landslide that they identified and defining exactly the sites. You see some cracks exactly correspond with the deformation pattern, so that's quite interesting. At the same time, so you have also time series, so you can identify that if there are correlations with some causes like precipitation and rainfalls. But of course, the same technology can be used in some cases even easily in urban areas. For example, that's a case in Poland. That's another one here in Rome, where you can detect what is going on in the surface due to excavation underground. And so that's an example. That's another one where, unfortunately, something happened. And you can see how, starting from this strange map, this is a radar map, you can reach this kind of information, where the colored points identify displacements, and green, as usual, means no displacement, while yellow and orange color means displacement. And in this case, we are in a city in Sicily. Something serious happened, and consider that this deformation were identified some months after that the problem occurred. But another example, similar of a tunnel, can be also not just in an urban area, but in this kind of environment. You see that, of course, when you have vegetation, you have less chance to get this kind of information, but something can be done, especially if there are few targets like buildings that reflect. And in this case, we analyzed something like 25 years of data, just being able to identify. You can see here of deformation since 1992 up to 2016, where you can clearly see that some buildings were completely stable, but after that some excavation work started, they started to move. And you have these two time series, one orange, one red, just because we used two satellites that were showing almost the same thing. However, this technology is also a great potential to better understand geological and geotechnical behaviors of a certain area, where, for example, a large tunnel has to be excavated. I think most of you, especially Italians, can recognize this site, even if there are these colored points above. That's Piazza Venezia in Rome, and that's the Altare della Patria building, a very famous building in the city center of Rome. And the color show movement. So again, green, no movement, and red and yellow movement. These results show that there is an overall area that is much more affected by movement than the other one. And when we compare these different patterns of these two areas with some geological features, some geological information, we recognize that there was an incredible correspondence between the area affected by deformation and the one affected by almost no deformation. Of course, the one affected by deformation were on soils much more compressible than the others. So that's a great example on how this technology can be used also to assess in some areas like this one, original condition and support also the geological investigation. So that's a new frontiers that can be achieved. So to integrate this data with standard information to increase the knowledge of the underground condition. And so that's again what I was mentioning as a knowledge monitoring solution. Then of course the details can be done like here, and as soon as you have high resolution data, like in this case, except in addition to this wide scale analysis, you can also go into a single building, like in this case, and recognize some specific points in these buildings and recognize what is the behavior of the building. In this case, for example, we see there is a long-term trend, quite small, but at the same time, there is some seasonal, cyclic deformation that are very useful for people that are planning to excavate a tunnel, because they know that there is a sort of conventional and standard behavior of that building. Another technology that, from my perspective, has a great chance to become a crack in the future, to detect crack as well, but also to check deformation. And the reason because it has several potentials that can use any kind of images. I mean, images from smartphones, photo cameras, cameras installed on the ground, also installed in a tunnel, or installed in a drone, or installed in a satellite. And using several processing technologies and several algorithms that are coming also from different fields from us, like spectral tracking, digital image correlation. I don't want to enter into much details, but just to let you know that combining all these technologies, it is really possible to use images to detect information, quantitative information about change and about displacements. This is just an example of what can be done using some rough resolution satellite images collected on this site. We are in Peru, and you just identify the movie of 1.5 years deformation of these landslides. We are in Archie. Of course, you can have a final example where, in addition to the color that is showing the amount of movement, you can also have some arrows that are showing the direction of movement. But the good point is that in addition to these good pictures, you can also have a time series for any point of any area. As you collected several images and you use these images, you can have this time series of deformation. And the same thing can be done with a ground-based camera, like in this case. It can be done for structures, like in this case. This technology is very good because it's not expensive. In some cases, of course, cannot be enough in terms of accuracy. And in that case, you have radar. Radar are much more expensive, on the other hand, but for serious problem or serious areas or critical areas, like in this case, you can easily understand the relevance of a site like this one and the relevance to control the pre-existing building before of the excavation of a tunnel. In this case, is an excavation of a station, so it's a very huge excavation site. I think all of you are able to understand where we are. If not, we are in Rome, in the city center, in the Foro Imperiale area, nearby the Colosseum. In this case, we use the ground-based radar using software developed in-house for the processing, and we are able to catch an image showing, fortunately, that everything was green. So no movement in different points of buildings and on the wall behind. Same technology can be used for 24/7 emergency and real-time analysis of landslides interfering with the tunnel excavation, with the entrance of the tunnel, like in this case. We are in Basilicata, in Molise and Abruzzo region. Of course, the good point of this technology that can work in any case, and it's able to identify in a few days if something is moving exactly the map of deformation of this site. And that was really useful, again, because for each one of these colored points, you have a time series with data every 5 minutes, 24/7, with any weather condition, including fog, including snow, and so on. And this technology was used for the first time in 2007. I'm getting to the end, but just to say that this is a technology that is quite potential, quite unusual still today, but the first application dates back more than 10 years ago. So it's so much consolidated with a lot of background in terms of scientific and technical background. And let's see, this first case was a tunnel, the entrance of a tunnel. We are in Calabria region. That's what's happened during the first excavation, few meters of excavation. What we realized is that in that slope, in addition to this relatively small collapse, there was a so huge landslide, 50 meters deep. There was a need for a real-time control during the excavation and the repairing works. So we installed for the first time in the world this instrument in this site, and we were able to control any movement and to detect time by time any kind of deformation caused by excavation works on the tunnel, action on the surface. And what is good is that at that time, we installed a camera. We installed a simple camera just to check what was going on the slope in terms of works, so that to better interpret the data. Today, with the capabilities of data processing of images, we take these images of 15 years ago, we processed, and we were able to catch the deformation of the slope just using the pictures taken by the camera. So that's everything for now. Thank you very much for your attention.
So, Professor, one of the questions is, what is the precision of the system?
I presented 3 different systems in general terms, so I will try to answer giving for all of them. For satellite technology, satellite INSAR technology, the precision can be on the order of a millimeter. So it's a millimetric precision level. For the ground-based radar, also 0.1 millimeter can be achieved, but of course it depends also on the distance, on the range distance, on the weather condition, and so on. But in general terms, 0.1 millimeter is something reachable. And for the monitoring, it strongly depends on the sensor. You can use different kind of sensors, so very close sensors can be very, very accurate, millimeter or less. If you look something from the sky with a coarse resolution satellite images, of course, can be on the order of several centimeters or decimeters. That's, anyway, strongly depends on what you use in terms of sensors and data.
Okay, so I guess we can for sanctions by Italian Association. hopefully we got through some little minor technological problem, but I think everything has been done very well. I hope that you could have listened to the presentation of the speakers, and that have been very interesting. So I would like to, well, give a little wrap up, but just saying that I'm sure that dealing with existing tunnels probably it's a more difficult job. It's a peculiar job because usually engineering society and design society are not so used to deal with them. It's easier to design and build new tunnels than to update new existing one, because you have to, of course, to have the knowledge of the one. So you have to understand the property, the geotechnical model, what's happened during construction. So of course, a lot of different things that it's not so easy to understand. And but I believe that we need to take care of the existing tunnels, and we need to have maintenance, repetition work, training, so the life cycle, let's say, of our tunnel. And I think that we need also industrialization process during construction, because I guess we should work more on industrialization of the construction, like, for instance, the example that I showed about Mazzanti tunnels or Montenegro tunnel, but we have to work on this also on smaller, say, little smaller work of rehabilitation, like milling of existing tunnel, waterproofing, and reconstruction of a new line. So this the main aspect that we had this afternoon with all the speakers. So I would like to thank all the speakers. So Professor Miliziano, Professor Giappirusse, Professor Paolo Mazzanti, and of course Marco Ranieri, which I shared the first presentation. So that's it, and I would like to say to everybody also, well, 1 week in advance, to have a good Santa Barbara on the 4th of December, and we'll host a special conference for that day with Professor Pelizza, who will have his lecture about historical tunnel, history of the tunnels on that day. So I invite you, everybody, to join this conference. It's completely free. So it's hope that you will be connected, of course, again on the 4th on the SIG platform, on the SIG channel, to attend to this conference. So thanks to everybody, and hope that it's been good. You had a good time, and we will take home with you some good information. Goodbye, everybody.